This is part of the BocaPhysics mini course on nuclear physics. Today is a continuation of the lecture on nuclear reactions. In particular, I'm going to discuss fission and fusion. The lion's share of the lecture will be on fission, with just a little bit about fusion at the very end. Before I get into that, though, I need to categorize neutrons into slow or fast, and then I also want to just cover briefly a few of the other kinds of reactions that slow neutrons can undergo. So what do I mean by slow and fast neutrons? Well, if you get into nuclear physics in a more serious way, these categories will be broken down even further. Thermal neutron has energy of 1/40th of an electron volt. That's about room temperature. An epithermal neutron has energy of about 1 electron volt. Slow neutrons have an energy up to 1 kiloelectron volt, and fast neutrons have an energy ranging from 0.1 to 10 megaelectron volts. And essentially, a lot of authors will just call all of these slow neutrons. But as I said, if you get into nuclear physics in a more serious way, they will distinguish between thermal neutrons and slow neutrons. Let's talk about a few of the processes that slow neutrons can undergo. There are 4 kinds of reactions involving slow neutrons. The first of these is radiative capture, and it results in the emission of gamma radiation and a daughter nucleus that has 1 more neutron than its parent. It's the most common kind of reaction because it occurs for both light and heavy nuclei. The next two reactions involve the emission of an alpha particle and a proton. These occur for light nuclei only. The final kind of reaction is fission. 2 fission fragments are produced, and they have atomic numbers ranging from Z equals 30 up to Z equals 66. Plus, neutrons are emitted as well. These are called prompt neutrons, prompt meaning that they're emitted at the time of fission. Now, radiative capture is the most common of those 4 kinds of processes, and the reason why is both light and heavy nuclei can undergo it. So let's take the lightest nucleus. Let's suppose that you have a reaction between a hydrogen nucleus and a neutron. What's the product of that? Well, we'll have a deuteron, and gamma radiation will be emitted. Now, the minimum amount of energy of gamma radiation is going to be 2.22 megaelectron volts. If you recall the first part of this lecture on nuclear reactions, we discussed photodisintegration. Well, this radiative capture is actually the reverse of that process, where you bombarded a deuteron with gamma radiation and you broke it apart. So, why is this useful? Well, let's suppose that you have a stable isotope, rhenium-103, say, and you bombard it with slow neutrons. What are the products of that going to be? Well, you're going to have rhenium-104. And of course, gamma radiation will be emitted as well. Rhenium-104 is an unstable isotope of rhenium. And you might want to use this if you're doing nuclear research. By the way, is it called, or it rather is a beta emitter. Now let's turn our attention to substances of more interest to us. Let's consider uranium-238. And let's suppose it undergoes neutron capture. And as a consequence of this reaction, the daughter nucleus will be uranium-239 and gamma radiation will be emitted. Now, there's also an important feature. This neutron has to have a specific energy in order for this process to occur, a certain resonance energy. Uranium-239 is a beta emitter, and it turns out the daughter nucleus of this process is going to be Neptunium-239, this is beta decay, an electron will be emitted and also an electron antineutrino. Well, the half-life of uranium-239 is pretty short. It's about 23.45 minutes. So this process won't take long to happen, on a human scale, I should say. Neptunium-239 is also a beta emitter. And its daughter nucleus will be plutonium-239. And that is a little bit longer, but not by much. It's about 2.35 days. So what's the importance of plutonium-239? Well, it's fissile material. So it's of interest to people who are building things that go boom. So you can start with a material that is not fissile, uranium-238, and by allowing it to undergo neutron capture, you can come up with a fissile material. Now, uranium-238 is not the only substance that can be used in this way. Thorium-232 can also undergo neutron capture, and its daughter nucleus is thorium-233. Thorium-233 is also a beta emitter. And the daughter nucleus of that decay will be protactinium-233, and of course an electron and an antineutrino. And that process only takes 22 minutes. Protactinium-233 is also a beta emitter. And the daughter nucleus, this beta decay process, is uranium-233 and an electron and an antineutrino. And that takes 27 days, so it's a little bit longer. Uranium-233 is also a fissile material, and plutonium-239 has a half-life of about 24,000 years. And uranium-233 has a half-life of 160,000 years, roughly, give or take a millennium or two. And both of these are fissile materials and can be used for some interesting purposes, shall we say. And a couple of other processes that slow neutrons can undergo, or reactions I should say, are proton emission and alpha emission. In the first case, if say boron-10 undergoes reaction with a slow neutron, well, an alpha particle is going to be emitted. And let's write that out. And the other product of this is going to be lithium-7. Now, protons can also be emitted, and for instance, that is, let's say we take sulfur-32, and the other product would be phosphorus-32. Now, as I mentioned, these occur for light nuclei only, so they're less common than radiative capture, which we just discussed. Now, the fourth category is fission, and I am going to be spending the lion's share of this lecture on fission, but before I get to that, I want to define what I mean by the term cross-section. So let's get to that next. The nuclear cross-section is a measure of the probability that a reaction will occur. It's defined as the rate of outgoing particles all over the current of incident particles and over the target nuclei shown to beam per unit area. It has units of area, so that's why it's called a cross-section. Oftentimes it's presented like it is the same thing as a geometrical cross-section, but in fact those numbers are usually different. So let's calculate the geometrical cross-section. That would just be equal to pi r squared. And the size of a typical heavy nucleus is in the order of 6 femtometers. So if I do the math here, it'll wind up as a number that's roughly in the order of 10 to the minus 28 meters squared. Now, meters squared are not a convenient unit to use, so I'm going to define the barn. And 1 barn is equal to 10 to the minus 28 meters squared. So the geometrical cross-section of a typical heavy nucleus is just 1 barn. Now, the actual nuclear cross-sections for uranium-235 and 238 are different. In fact, for fission to occur, and that's the reaction of a neutron, a slow neutron, with uranium-235, that's equal to 584 barns. Another process that can occur is radiative capture, and that's roughly equal to 100 barns. Actually, it's a little bit less than that. It's probably closer to 97. Anyway, the cross-section for uranium-238 is going to be 0 barns, so the Coulomb barrier to be overcome in order for the fission reaction to occur. Uranium-235 does fission, uranium-238 does not, so this is 0 barns. However, uranium-238 can undergo radiative capture, and the cross-section for that is 2.8 barns. So the nuclear cross-section is not the same thing as geometrical cross-section, as we see from here, because the actual geometrical cross-section is a lot smaller. When the cross-section is bigger, that means there's more of a probability for a specific nuclear reaction to occur.
Let's take a look again at the binding energy per nucleon figure. The maximum binding energy per nucleon occurs for around A is equal to 58. The curve climbs steeply as you go to the right until you get to A equals 58, and it climbs gradually as you go to the left, starting from the far right of the figure. Fusion is favored to the left of A equals 58, and fission is favored to the right of it.
Let's suppose that uranium-238 spontaneously fissions. And let's suppose further that it breaks apart into 2 equal fragments. Which would mean that it would break apart into plutonium-119. I want to figure out how much energy is released in this fission. Well, to do that, I'm going to calculate, again, the binding energy per nucleon. Binding energy can be calculated from the atomic number times the mass of hydrogen plus the number of neutrons times the mass of the neutron minus the mass of the atom in question. So for uranium-238, that is going to be 92 times 1.007825 atomic mass units plus 146 times 1.008665 minus the mass of uranium-238, which is equal to 238.050788, and we want to multiply that by a conversion factor, and without putting all the steps in there, basically it's multiplying by 931.5 mega electron volts. And that's equal to about 1802. Oops, jumping the gun here. Binding energy is equal to 1802 mega electron volts, but we are interested in the binding energy per nucleon, so this is divided by 238, and that gives me roughly 7.6 mega electron volts per nucleon. And we do the same thing for palladium-119. Let me read this off. This is 46, the atomic number of palladium times 1.007825 plus 73 times 1.008665. Again, this is the mass of hydrogen, and that's the mass of the neutron, minus the mass of palladium-119 is 118.923340, all times 931.5 mega electron volts. And I'm going to do the math. Equal to about 996 mega electron volts, and I calculate the binding energy per nucleon. So divide this by 119. I wind up with 8.4 mega electron volts per nucleon. So there's a difference in the binding energy per nucleon depending on whether you're at the high end, very high end uranium, one of the isotopes, or if you're in the middle part of mass numbers. So essentially the energy released is going to be roughly equal to 0.8 times 238, and that's going to be equal to roughly 190 mega electron volts. And that's typical for these kinds of fission processes. So basically, you say, well, it's about 200 mega electron volts of energy are going to be released in any kind of fission reaction. If you do the calculation for uranium-235, you'll get about the same numbers, same ballpark. So this sounds great because 200 mega electron volts of energy released in this fission process versus 20 mega electron volts in other kinds of nuclear reactions. Hey, that's a great amount of energy, and it looks like right here, all you'd have to do is just have fuel consisting of uranium-238, and it's naturally occurring uranium is 0.72% U-235. So you have all this energy release. You won't have to do anything. However, these processes are rare in comparison. Remember, we talked about the natural radiation series at the top of this lecture. talked about U-238 and showed how it decayed and how all of its descendants decayed. We did the same thing for U-235 and also thorium-232 as well. The way uranium-238 and uranium-235 are likely to decay is by alpha decay. So that's overwhelmingly what would happen if you just left uranium-238 and 235 sitting out there somewhere. It usually undergoes alpha decay. Chance, or the likelihood of these isotopes spontaneously fission, are really just a small percentage of all decays that occur. So the question is, why is that? And for that, we need to look at the potential energy that these nuclei experience. So, potential energy looks something like this. Outside goes as 1 over r. And that's because here, Coulombic repulsion dominates. Inside, the strong force dominates. So right around this region, it's roughly where the two nuclei are very close together. I don't use the word touching, but say that that's the radius of nuclei 1, or nucleus 1, that's the radius of nucleus 2. There's going to be a Coulomb barrier. There's going to be a Coulomb barrier that, that these nuclei, these fragments, would have to overcome in order to actually break apart. The difference between the bottom of this one and the top is called the critical energy, and some other authors use the term activation energy. So when either uranium-238 or 235 are sitting, they don't have enough energy to get over this Coulomb barrier. Now, classically speaking, it would be impossible for these particles to get through this barrier. Quantum mechanically, it is possible. And if you've ever studied quantum mechanics, you've undoubtedly talked about tunneling. So there's a small probability that tunneling could occur, and that's why uranium-238, 235 do sometimes spontaneously fission, albeit rarely. Okay? So the question is, how in the world can you cause uranium-235, and as it turns out, this will not be the case for uranium-238, how can you cause it to have enough energy to get over this Coulomb barrier? So, one way of doing that is to allow a neutron to react with uranium-235. And therefore, those two quantities, or these two, I don't want to say particles, but the nucleus and the neutron together will form a compound nucleus, uranium-236, and it will be in an excited state. Calculate how much energy is associated with the excited state. So what's the excitation energy? So these two particles together times c squared will give you the energy of uranium-236 when it's in an excited state. So if we do the math here, mass of the neutron once again is 1.008665 plus mass of uranium-235 is 235.043930, and minus the mass of uranium-236 when it's in the ground state. And again, I'm just going to convert this over directly, so that amounts to multiplying all of this by 931.5 mega electron volts. And do the math, that's about equal to 6.5 mega electron volts. So that's the excitation energy. And plus, we're excluding the possibility that this neutron has any kinetic energy. So essentially this is a calculation if you're assuming that the neutron has zero energy, okay? Or this is a thermal neutron, in which case we're talking about an energy on the order of 1/40th of an electron volt, which is not really going to, it's not going to change this calculation at all. So the excitation energy is 6.5 mega electron volts. Now the energy necessary for uranium-236 to get over this Coulomb barrier is around 6.2 mega electron volts. So voila, just by putting uranium-235 in the presence of thermal neutrons, remember we just talked about cross-sections, cross-section of uranium-235 regarding the capture of a neutron and hence forming this uranium-236 in an excited state, that's very high. So this is the excitation energy that this nucleus has, and the activation energy is only 6.2, so therefore fission can occur. So fission will occur here. Now what about uranium-238? We were just calculating binding energy. What's the excitation energy going to look like in that case? Well, do the same kind of calculation, calculate the sum of the masses of the neutron and the uranium-238 nucleus, and take the difference with uranium-239. Mass of the neutron once again is 1.008665. Mass of uranium-238, 238.050788, and the mass of uranium-239 is 0.0 239.054293. So let's do the math once again. And this time I'm going to wind up with 4.8 mega electron volts. Now the activation energy necessary for uranium, the compound nucleus of uranium-239 to get over this Coulomb barrier is in fact higher than 6 mega electron volts as well. So there's not enough energy there for this nucleus to break apart. However, if this neutron actually had energy, if it weren't just a slow neutron, or certainly not a thermal neutron, not even a slow neutron, but a fast neutron, say of 1 mega electron volt, or a little above that, then it could get over the Coulomb barrier. So this is why uranium-235 is used as a fuel in nuclear reactors, because by allowing uranium-235 to react with thermal neutrons, results in a compound nucleus that's in an excited state with enough energy to get over the Coulomb barrier. Okay? So the next question is, what does this break apart into? As it turns out, there are actually many different ways that fission can occur, and let's just look at a couple of those next. So one such process is that uranium will fission, nucleus will fission into barium-141, krypton-92, and an additional 3 neutrons will be emitted. And these are called prompt neutrons, meaning that they're emitted at the time of fission. I want to calculate how much energy is released in this particular reaction. And as usual, of course, these are in atomic mass units, and you're going to multiply by a conversion factor, which gets rid of the atomic mass units, and times c squared. It results in basically multiplying by 931.5 mega electron volts. Let me just read this out. This is a mass of the neutron, 1.008665, plus the mass of uranium-235, 235.043. 930 minus 140.914403 plus 91.926173 plus 3 times 1.008665. 8665 all times 931.5 megaelectron volts. I just write the answer down on the board, is 173 megaelectron volts. So that's one possible way the fission process could occur. Another way is it can break apart into rubidium and cesium. Plus 2 neutrons. So how do you know which way a uranium nucleus is going to break apart? Well, you don't. Let's take a look at a diagram that shows the yields of the fission products.
These are the beta decay series for the fission fragments barium-141 and krypton-92. Barium-141 is neutron heavy, and so undergoes beta decay, resulting in the daughter nucleus, lanthanum-141, which has 1 more proton and 1 less neutron. Lanthanum-141 in turn decays into cerium-141, which again has 1 more proton and 1 less neutron than its parent. And this particular series ends with the stable nuclide praseodymium-141. The second series begins with krypton-92, which decays into rubidium-92, which decays into strontium-92, which decays into yttrium-92, and ends with the stable nuclide zirconium-92. Notice in each of these series, the duration of half-life increases as the series goes to the right. We just looked at one possible way of uranium-235 undergoing fission, which resulted in the fission fragments barium-141 and krypton-92. However, uranium-235 undergoes fission in more than 30 different ways. This diagram depicts fission yield in percent versus mass number. In front of this diagram, we see that fission fragments most likely will have mass number 95 and 139. Moreover, uranium-235 is neutron heavy. The ratio of the number of neutrons to the number of protons is roughly 1.6. Consequently, its fission fragments will also be neutron heavy. In order to reach stability, these fragments and their descendants will either undergo beta decay, as we just saw with barium and krypton, or they'll emit additional neutrons. These neutrons that are emitted after fission occurs are called delayed neutrons. Where does the energy go? Suppose 200 megaelectron volts of energy is released altogether. The kinetic energy carried away by the fission fragments might amount to around 167 megaelectron volts. Fission neutrons carry away 6 megaelectron volts of energy, and in addition, immediately after fission occurs, gammas carry away 6 megaelectron volts of energy. As we saw, the fission fragments are neutron heavy and so undergo beta decay. So that amounts to 5 megaelectron volts, and additionally gamma rays might be emitted as well, carrying away an additional 5 megaelectron volts of energy. Now neutrinos are also produced as a consequence of beta decay, and they carry away 11 megaelectron volts. However, this energy is lost because neutrinos interact only very weakly with other matter. Now please note that these are ballpark figures, but they are typical of fissions.
Roughly 2.4 neutrons are produced on average for every fission reaction. And the reason why this isn't a whole number is because there are a bunch of different ways that uranium-235 can break apart, more than 30 in fact. So sometimes 2 neutrons are promptly emitted, sometimes 3. But on average it's 2.4. For other fissile material, for instance plutonium-239 and uranium-233, you have comparable numbers of neutrons being emitted. So those neutrons that are emitted are now available to cause further fissions with other uranium-235 nuclei. And those fission reactions take place, more neutrons are emitted, and the process continues. And that is what is meant by a chain reaction. The way of quantifying that is via the quantity K, which is sometimes called the multiplication factor, or sometimes called reproduction factor. And it represents the number of neutrons available to the next generation. There are two main areas of operation when k is less than 1. This is termed the subcritical region. And that means there aren't enough neutrons to sustain the chain reaction, and therefore it will end. And you will also have the supercritical region, where there are certainly more than enough neutrons to sustain the chain reaction. And right in between these is called the critical. I don't want to use the word region, but I will. And that means there are just enough neutrons to sustain the chain reaction. Now, looking at this 2.94 neutrons being produced on average would seem to indicate that operation of your nuclear reactor would automatically be in the supercritical region. However, some neutrons are lost or leak out. Others are absorbed by the moderator. So what's the moderator? Well, essentially its job is to slow down neutrons. Neutrons that are produced as a consequence of the fission reaction are not slow neutrons. Their energies are too large. And remember, the cross-section for uranium-235 is very large for the absorption, or I should say for the fission reaction to occur with slow neutrons. So those neutrons that are produced have to be slowed down. Ideally, your moderator would be cheap, abundant, and itself low neutron capture cross-section. And some candidates for that would be just plain old water, heavy water, and graphite. Okay? So, if your reactor happens to be in the supercritical region, that means that the number of reactions can go up exponentially. So let me show that to you right now. Unfortunately, I'm going to have to erase this, but I'll just leave it up here for just a little bit longer. Again, moderator, the job is to slow neutrons down such that they can be absorbed, or rather react with uranium-235 nuclei, forming uranium-236 in the excited state, a compound nucleus essentially, which then fissions, fragments are produced as a consequence of that, as are additional neutrons. Okay, so let's say N here represents number of neutrons. Now in the reaction equations I've used N to represent neutron itself, but now it means number of neutrons. And we'll also introduce a new quantity, tau, which is a time constant. And that's indicative of the time between generations. I'm going to write down an expression that governs this process. The number of neutrons produced in a certain little time interval would be equal to n times k minus 1. Again, we're subtracting off 1 because 1 neutron is needed to cause the fission reaction to occur, dt over tau. I solve this. This is just dn over n. K minus 1 times dt, let me rewrite that, it's a little bit sloppy looking, over tau, and I integrate. This will be natural log n over n naught, where n naught represents the number of neutrons initially, and this will be k minus 1 times t over tau. It's k minus 1 again because, again, one neutron has to go in to cause the reaction to occur. So I take the exponential both sides, and basically this is n is equal to n naught e to the k minus 1 t over tau. So I can see that if k is equal to 1, this is just going to be e to the 0, which is just 1. So critical operation means the number of neutrons is going to remain the same. K less than 1 would mean that this exponential would be e to the minus something or another, so the number of neutrons is going to decrease. And here in the supercritical region, the number of neutrons is going to continue to grow. And if k is much, much bigger than 1, well, then you have a... But basically, if you want to have a nuclear reactor, it's actually going to be right around 1. This is where the difference between prompt neutrons and delayed neutrons becomes important. Prompt neutrons are produced at the time of fission or right afterwards. Delayed neutrons might be emitted a little bit further down the chain. So this occurs on a much slower time scale than the prompt neutrons do. So how you'd operate a nuclear reactor is have the number of prompt neutrons just below the critical region, just barely subcritical. And your delayed neutrons would be a little above that. Because the reason why you want to do that is because delayed neutrons are a little bit easier to handle. See, if you're in danger of getting into the supercritical region, you use control rods. And if you insert more control rods, they're neutron absorbers, that will drive the value of k down. And if you, in the subcritical region, you don't want to remove some of the control rods to push k up a little bit. And so, as I said, it's easier to deal with delayed neutrons. We're talking about a little bit slower time scale that can be handled better. Okay? Now, as far as the moderator, I mentioned that you have water and heavy water. Water is just plain H2O, and heavy water is D2O, or D is just deuterium. If you want to use plain old water, means you're going to need to use enriched uranium, so 3%. Remember, the natural abundance of uranium-235 is about 0.72%. And for uranium-238, it's 99%. And then the other isotope, uranium-234, takes up just a little bit of natural abundance. If you use heavy water, you can just use just natural uranium. That's why you have a heavy water plant. Heavy water is a moderator, so you can use natural uranium. You don't have to enrich it. And 3% figure brings me to an interesting geological event. One that took place 2 billion years ago. And at a place called the Oklo site. And what the geological event was is that there were actually natural fission reactors. I believe there are about 9 of them that have been discovered. This was discovered by a team of French scientists back in the early 1970s in the Republic of Gabon in Western Africa. And if you watch the video on the exponential decay law, I worked through an example where I compared and contrasted the features of uranium-235 and uranium-238. Essentially, we assumed that, or actually it is assumed, not just we, that uranium-235 and 238 were created in equal abundances. However, because the half-life of uranium-235 is smaller, so it's roughly 700 million years, and uranium-238's half-life is roughly 4.5 billion years. Because these were formed in equal abundances, because the half-life of uranium-235 is less, more of the uranium-235 is decayed away. And now this is why we have present abundance naturally occurring of 0.72%. However, 2 billion years ago, the natural abundance of uranium-235 was 3%. So at the Oklo site, there happened to be groundwater, and the groundwater there served as a moderator for the nuclear reactions that occurred. So basically, this process went on for, I think the estimates range from 500,000 to several million years. And I think there's a tendency for people to think that fission reactors as being unnatural and man-made, but there were natural fission reactors here on Earth in operation several billion years ago. Now, there's a practical side to this research as well, not just, wow, isn't that neat? And the important practical feature has to do with the storage of radioactive waste for present man-made reactors. You see, there wasn't a lot of migration of the fission products. They mostly stayed confined to the area. So that's good news. The idea of storing radioactive waste means that that can be kept confined without worrying about it leaking out into the environment. Now, you do have to keep in mind that the radioactive waste that's handled today, it's different, obviously. There are some differences between this and what occurred naturally at the Oklo site over the past few billion years. But nevertheless, I think that's good news regarding the storage of radioactive waste. And there is one last topic that I want to get to, and that is fusion. Building a fusion reactor has proven to be a much bigger technical challenge than ever building a fission reactor, and the reason for that is a Coulomb barrier that has to be overcome. Essentially, the temperature of the fuel has to be at 10 kiloelectron volts, and in the field of fusion, you speak of temperatures in terms of electron volts. Now, the energy is equal to Boltzmann constant times temperature. Boltzmann constant is 1.38 times 10 to the minus 23 joules per Kelvin, and if we do the math, see that 1 electron volt is equivalent to 11,600 Kelvin. And that means this temperature is on the order of 100 million Kelvin. So the problem is, how do you contain something that's that high a temperature? And essentially, fusion is light nuclei. So light nuclei have to be at this temperature, And this means that they're going to be fully ionized. So basically, the fuel, if you will, is going to be in a plasma state. So the field of fusion research really is the field of plasma research. And it becomes a question of how do you heat a plasma or heat fuel to these temperatures. And how do you confine it? Or how do you contain the plasma? And there are two ways of doing it, basically. One way is via inertial confinement. And the other way is via magnetic fields. Most of the research has gone into studying how magnetic fields can confine these very high temperature plasmas, and such devices as accelerators and tokamaks were constructed for that purpose. And it goes beyond that into questions of equilibrium and stability. So I'll just wrap this discussion up with three processes, fusion processes of interest. In this case, you'd have the fusion of two deuterium nuclei, and they would produce a tritium, or a trigon, tritium nucleus, and a proton, or hydrogen nucleus. Another process that occurs is that the two deuterium nuclei combine to form a helium nucleus and a neutron. And finally, you have deuterium undergoing fusion with tritium to produce an alpha particle and a neutron. I'm going to calculate the energy released. And we'll just do the last one. Remember the mass of a hydrogen 2 atom, deuterium atom, is 2.014102 atomic mass units. Mass of a tritium atom is 3.016049 atomic mass units. Mass of helium 4 atom is 4.002603, and finally mass of a neutron is 1.008665 atomic mass units. I'm going to do the math here. Add up these two masses and subtract the sum of these two masses. And when I do the math, I'll see that 17.6 mega electron volts of energy is released. And you can do the same thing for these two other nuclear reactions to see how much energy is released there as well. But anyway, as I said, getting a fusion reactor to work here on Earth is extremely difficult, very difficult technical problems that have to be overcome. Really, fusion research boils down to plasma research, and that belongs in its whole other course. So I'm just going to leave it there, and this concludes the BocaPhysics mini course on nuclear physics.